So I'm Colin Slater. I work with Eric Bell at the University of Michigan. I'm going to talk about the Monoceros, as seen in Pan-STARRS 1. So this is work that's been done with the Pan-STARRS Milky Way group, who I've listed some of their names here. But also I owe lots of credit to the entire Pan-STARRS consortium for building a telescope and running a pipeline and getting us all this great data. So to make sure that we're all on the same page, I should start with the figure that we've all seen and that we all like in this field. This is the field of streams from SDSS. So this is just a map of main sequence turnoff stars in the galactic halo, and they're color-coded by distance. So we see sort of standing out in red and yellow and green is the Sagittarius stream, because Sagittarius is huge and just covers an enormous piece of the sky. You also see little things like PAL 5 and the Orphan stream, and a whole bunch of small dwarf galaxies standing out as little spots. But if you look towards the galactic anticenter, sort of on the far right side of the plot, there's a sort of blue haze fluff thing. And that's what we call the Monoceros ring. Oh, I got it. Yeah, I don't know how to operate it. Sure. So it's at sort of high latitudes. It's towards the disk, but Sloan only surveyed down to sort of B of 30 degrees or so. So it's really up higher than we would expect, like a disk just to be living. So it seemed to have been some sort of overdensity here. But as you can see, that this is really the best picture that existed of Monoceros, and it's incomplete. It goes off the edge. We don't really have a full picture of what it looks like. So this has led lots of controversy. It doesn't look like a stream, like Sagittarius. Sagittarius looks like a stream. Monoceros, it's less clear. Is it a disk? Is it sort of some weird thing about the disk that we don't understand? Is it some sort of weird stream that we don't understand? Where does it come from? Where does it go? All these questions are just unanswered by Sloan. And so that's sort of questions that are specific to this one feature in the Milky Way. But more generally, we'd kind of like to know, what do disk-satellite interactions look like? What do satellites do to the outskirts of the disks? We don't have a very good handle on this because we don't have a lot of examples, but Monoceros is one. So we'd like to know, is this common or is this rare? And to do this, to really know what's going on here, we need good examples, so like Monoceros, and we need good simulations to help us understand these examples that we see. So let's go on to the Pan-STARRS data. This is in RA and DEC. I'm going to reorient you all into galactic coordinates to make this easier to look at. And so the part of Monoceros that we've known is going to occupy this little portion of the screen. But Pan-STARRS has this enormous 3/4 of the sky footprint. So when I make the same map with Pan-STARRS, we get this huge map. And I'll get rid of the Sloan. You see in green, you get the same basic three sort of arcs, these overdensities that are extending up way above the disk that we saw in Sloan. So we see the same thing there, but we also see that extends to both sides, left and right here, over, like, this is 100 degrees, so it's very long. And I'll just have some little bars to highlight the sort of features that we're looking at. You see there are also these sort of sharp edges, sort of telling us that it's something dynamically cold. This is not just an exponential disk that's kind of fading away. There's actually a sharp feature here. And the coolest thing about the Pan-STARRS map is that not only do we see that Monoceros exists up here in the north, but we see the same sharp edge feature in the south. Basically, it just looks like a reflection of Pan-STARRS in the north, but on the other side of the disk. And we've never had a map like that before. This is the first time we can say that Monoceros clearly has a sharp edge on both sides, north and south of the disk. So those are the features that we see. And it is quite large. And just to fill in, if it was just an exponential disk, you would really see the density start to sort of taper here and taper here, but the sort of puffing up sort of 60 degrees tall is really unique to the Monoceros ring. That's the view inside of the Milky Way disk. it's nice to sort of think about this schematically for what would we see if we were outside of the Milky Way. So I've actually drawn this to scale to the best I can. So Monoceros is something like 8 kiloparsecs away from the sun, so twice as far as the sun is from the galactic center. But then just doing basic geometry of it's at b of 30 degrees and it's at 8 kiloparsecs means that this is a really tall feature. It's 5 kiloparsecs above the disk. It's huge. So if this one typically imagines like, oh, galaxies might flare in the outer parts of the disk, but that's just, usually flares are sort of a few scale heights, or the scale height increasing by a factor of a few, but not 5 kiloparsec jump all of a sudden. And there might be some hint that there's a distance asymmetry, so I kind of suggested that, but we don't have the perfect distance indicator, so that's a little less certain. So, giant feature. So we have all this morphological information. We have this very nice map. We can actually see what Monoceros looks like now in a way that we couldn't before. How do we use this? So I said earlier that sort of simulations are the key to understanding what caused this feature and why it looks the way it does. So I'm going to show two models where we've sort of taken, these are models that existed prior to the Pan-STARRS data, so they were designed to reproduce what was known in Sloan and from other studies. And we're just going to show them show them in the same way that I show the Pan-STARRS data, and to see, well, how well do they do at reproducing what we see on the sky. The first model is an accreted satellite. So in that, there's a dwarf galaxy that came in sort of parallel to the disk, and all the stars in Monoceros are just from that dwarf satellite. There's no disk in this model. In the other case, the disk itself, the Milky Way disk, has been sort of disrupted by dark satellites or something. Something has perturbed it, so it's only disk stars that cause the feature. So this is the accreted satellite model from Penny-Rubia et al. This is the observations on the left and the models on the right. So I've plotted them the same way. I've made basically the same sort of distance cuts. Tried to reproduce it as closely as I can. I just sort of marked the arcs where we see Monoceros in green here. And so we do get a nice stream in the south, a nice stream in the north. That seems to sort of reproduce the basic overall idea of Monoceros, which is what it was designed to do. So it's good that it does what it's designed to do. Looks pretty good. The downside with the accreted satellite model is that if I have a satellite galaxy that's falling into the disk, it leaves a big, long tidal stream, and that stream kind of has to extend beyond sort of larger galactocentric radii. So if I go make a map at a larger distance, this is going out to sort of 14 kiloparsecs from the sun. I see kind of the same thing. I see this is actually Sagittarius there, but nothing really new is popping up. I don't see any other parts of a tidal stream that I didn't see before. But if I look at the model, then I have all sorts of new features coming in. So this feature diagonal, that didn't exist before. They're new parts of the stream that I don't see in the observations. And so to sort of fix this up, one has to hide those or do something to make the outer parts of the tidal stream sort of not be visible. So this model, some good things, some bad things. It's not tuned to reproduce this, so I don't want to fault the entire idea, but that's just sort of what we have at the moment. So the other model, if I just take the Milky Way disk and I sort of disrupt it with satellites. Now we're not looking at the satellite stars, we're just looking at the disk. This is from Katzenzitis et al. So again, the observations on the left, and here's the disk in this model. You can see that it's really been sort of warped up to 20 degrees, 30 degrees above the plane, which that's the right height we need, but you can see that like there's no material left at b of 0. It's basically taken the entire disk and sort of shoved it up to higher, greater heights. And so that's maybe a little too much destruction of the disk. It also doesn't reproduce the asymmetry, so we don't see any material down in the south. So this was a sort of, I believe this was found serendipitously in a set of simulations. So I don't want to, this is not necessarily a problem with this entire category of models, but this does sort of say that, well, we need to do some more kicking up to higher heights, but we need to still keep a disk that remains mostly intact. So again, some good features, some things that sort of future iterations of these models would need to improve on. So we have some first attempts at decoding Monoceros, but we don't have answers yet. This is still sort of evading any explanation. And we really have way more data than we really can interpret with the models. These are sort of the best examples that we had of simulations to reproduce Monoceros, and they don't quite cut it. So we need to sort of be going towards the model direction to have a better idea. And to do so, I'll just hint at what we're working on at the moment, is we're trying to resolve this more with cosmological simulations, where maybe this wasn't fine-tuned to reproduce Monoceros, but we might be able to find some features that kind of resemble sort of Monoceros-like structures. So I'll just hint at some of the examples that we're doing. This is just a suite of 6 example simulations from Marie Martig, and just to get at the hint of all the variations that happen in these simulations. You get big disks, you get disks that disappear, you get lots of streams, you get no streams, you get sort of a stream of satellites, you get some sort of fluffy stuff. We haven't gone into every single detail of these, but there's a wide variety of morphological features, and we're still looking for them. So I'll just end on the pretty picture. Thanks.
In the simulation model, there are many parameters to look through the suburban orbit or something like that. So I think it's difficult to look through the vast parameter space. So I think many parameters are left to be discussed. So how robust is that?
I agree. There are way too many parameters to tweak, which is why we've been looking at finding cosmological simulations where we just sort of make do with whatever parameters happen to be, or whatever happen to be in that galaxy. And then maybe once we have a handle on that, maybe some sort of guidance from the uncontrolled experiments, then we'll be able to go in and tweak controlled experiments to more accurately reproduce Monoceros. But that is basically the problem.
Monoceros, actually, the stream with the other streams actually has some effect on it as well. So there's actually a crosstalk between the streams. Some region it's not double checked by the velocity.
I'd worry slightly more about the satellites from the other streams sort of interacting with the stream material. So maybe the Sagittarius dwarf interacted with the Monoceros stream material. Certainly could be possible. I don't know if stream versus stream itself does a whole lot, just because there's not a lot of mass.
Well, I have a crazy question, how for you and how for Avishai. Earlier, we started today with seeing all this mess of very, very compact streams inside the halos of galaxies. Why can't the streams be an inheritance of the streams directly, rather than having to pass through a visualized phase, be a dwarf, and then being disrupted? Do we resolve the streams well enough to know that they don't keep, because they might be dynamically cold memory inside the halo of a galaxy? Would it matter for what we interpret? Because in a sense, if we disrupt the dwarf, might mean something. If we don't disrupt the dwarf because we never made the dwarf, might be interesting. So I don't know if the simulations are good enough for us to see whether we could do stream formation in the streams.
There are no young stars in Monoceros.
Well, I'm not talking about this particular stream, but my goodness, indeed, it's a field of streams. And it's a very, I'm curious about this question. Might be. Anyway, let's thank Colin again, and